Okay, nice session to be in. I want to start by thanking Florian and Clara for putting together this. Notice there's no light in the name of this. And one thing I really love about this field is that there's so many different substrates going on. And I'm seeing over the time that I've been in this field, the emergence of this common language. And I thought the first talk in the session, and actually the second talk too, were really good demonstrations of that. So I will try and follow in their footsteps. And although I will talk about photonics, I hope that it is something that is accessible to everyone in the room, and you can learn some lessons from it. And then the second part of the talk, I'll even generalize it to physical neural networks in general. Oh, and by the way, if you want to download the slides, you may want to do that, especially if you're someone that likes to read all the slides, because I tend to move pretty fast. So I recently moved to Yale, and as you can see, we have a wide open table, which has now been filled over the last year or so. We're working on a wide variety of different things, but I'm going to concentrate on work that we're doing related to photonic neural networks here. So at the beginning, I want to introduce the possibility of something that would be very exciting if it takes place. And the main thing I want you to understand is just that this could happen and why it could happen. It's an interaction between people like us, academics doing research, and business, the big moving machinery of companies like NVIDIA. In part two, I'm going to comment on how we as academics doing physics research might be able to affect this big moving machinery of companies like NVIDIA and actually make something like this transpire. And then I'm going to generalize this to the case of physical neural networks or physical computer science or physical learning, what have you, and offer my perspective on what I think this could look like there. So some disclaimers. This is mainly me pointing out a trend and opportunity and how I think we should think about it. I'm not saying that it will happen. In fact, I think it's not likely to happen. I think it's maybe 25% odds. I'm also going to feature my own work as examples throughout. Actually many groups, not just the groups that are here, are working on this. And importantly, companies are also working on this. In fact, they're probably doing the most important work. Okay, so the first part of the talk in one slide. Historically, better computers and better integrated electronic systems have reinforced one another. And there's a positive feedback loop between these two that have given rise to increasing value, right? So more money is being made and more resources is being poured in to make better electronics. And I call this a virtuous cycle in contrast to a vicious cycle. And photonics is allowing for computing systems that do more by providing broadband, low latency interconnects. And this is already happening inside data centers. But it presents an opportunity, perhaps, for optics to contribute something else, namely better scaling analog compute. Photonics, if it were to become integrated into computer systems sufficiently intimately, would expand the domain of what we consider computation. And this is true of all physical analog computational systems that are not digital electronics. It would allow us to think about applications of computers that are not merely processing digital data. And I'll give you some examples of that. And if everything went well, at some point photonic technologies would be integrated into this technology business cycle, and that would elevate the field in a way that I think is difficult to imagine. And then finally, if this were to transpire, we actually have the power to affect it. And I think one of the main things that we're not doing is thinking about how to ease the transition from the current status quo to this possible future. So let me start with the current virtuous cycle. So historically, better electronics have allowed for better computers. And because computers are a general purpose technology, there's been two modes of better computers leading to more profit. One is that as computers get better, existing users become more happy and they want to buy a new computer, right? They can do their simulations, their neural networks, or their video games better, so they're going to buy the next one. But the more important thing is that as computers get better, because they're a general purpose technology, you see the emergence of new applications. So the customer base grows, and as a result, we're not just seeing customers continuously providing money for the next computer, we're actually seeing the pool of customers grow. And this gives rise to more resources, which get funneled into building better electronics, and so on and so forth. So the virtuous cycle is not a feedback loop like this, right? It's not a closed loop. It's actually a spiral of ascending profit and resources and technological capability. And this has created a truly uncanny situation for digital microelectronics, right? It's not been cheap. There's at least $6 trillion that have invested into making this possible. But on the right-hand side, you can see what this has enabled, right? Transistors have shrunk by 10 million times. They've become nearly 1 trillion times more reliable. And we've seen the growth in the number of transistors per chip by 10 to the 11 times, right? If you were to put numbers like this in the discussion section of your paper and say, maybe in 20 years we could improve this by a factor of 10 to the 10, you would be laughed at. But the virtuous cycle made this possible, and we all have benefited from it, from the devices that we have here, in all your pockets. I think the best way to see the fruits of this is to see that this is a science experiment here. This is the famous crystal triode, right? The first transistor at Bell Labs. And on the right here, this is an image of a relatively old Intel processor, which we're going to zoom into. And you can see we keep zooming in, keep zooming in. This is the level of sophistication of systems that are created now in digital microelectronics. And when I think about what would happen if another physical substrate were to be elevated into this virtuous cycle, I think about the spectacular capabilities that would be possible if we could have photonic systems or superconducting systems or analog electronic systems that had that level of sophistication. So the virtuous cycle proceeded pretty merrily along from the 1970s into 2004 by something called Dennard scaling, where as you scaled transistors down, you were able to make them faster and they could consume less power per unit density. But around 2004, this switched. There were physical limits that became impossible to circumvent. And as a result, what has happened is we've instead increased the size of the computational system. So we've gone from Dennard scaling to the era of multi-core processors and then to GPUs. That is, we're having more transistors integrated into a computer. And GPUs take this to the real logical limit, or maybe the illogical limit. This is the Blackwell chip. This is actually 2 reticle-limited dies. So this is larger than anyone would have ever reasonably expected a computer chip to be, but NVIDIA is making them, and it's perhaps the most important product in the world. And this makes data movement across the chip an increasingly large concern. So we've seen breakthroughs in industry on electrical interconnects. And of course, optics, which is already in the data center, is being considered for more and more communication within computer processors. So let's talk about these interconnects first. So the idea of optical wires in computer systems is not new. In fact, it wasn't even new in 2000 when David Miller wrote about it eloquently here. But I recommend reading this paper by David, which really lays out something that took 25 years to finally start materializing. In this paper, David analyzes the bandwidth, that is the information that you can send through an electrical wire per unit time. And he shows, rather simply, that it scales with the inverse of the length of the wire squared. And if you know how optical waveguides work, you'll recognize that this is not the situation in a dielectric waveguide that we normally use for light. This, to first order, has a bandwidth which does not scale with the length. So if you plug in these formulas and you look at the bandwidth in bits per second versus the length of the wire, these electrical wires fall off in bandwidth, whereas the optical wire remains constant. Now, these are just back-of-the-envelope calculations, but they give rise to a conclusion which I think is fairly well known. That is, once interconnects reach a certain scale, around a millimeter, even hundreds of microns, it becomes sensible to start considering using optics. And currently, optics is used for distances like this, or across the ocean, but it may start to make sense to integrate it into computers because this is the size of the Blackwell chip. And this is the size of the Cerebras wafer scale engine, which is a serious ASIC for performing AI. And you can see here, this is the Blackwell chip. This is an entire wafer scale chip. So in industry, there's a lot of development. And I'll just give you a few examples. IR Labs is a company developing silicon photonics. They're doing micro-ring modulator-based interconnects, right, for connecting chiplet systems together, among other things. Google, with their TPU, which is the main competitor to the GPU, in fact, a very successful competitor so far, introduced optics into their TPU cluster using this optical circuit switch, which I was quite surprised when I first found out. It actually consists of just two DMD devices, but there are tens of thousands of these in the world now, and this is really actually leading to a lot of development and competition in developing optical circuit switches. But for me, the thing that was most inspiring, the thing that made me really think that something special could happen for photonics, and you saw this in Dimitri's talk at the beginning of the workshop as well, is that NVIDIA and TSMC are committed to developing co-packaged silicon photonics. They are not currently doing this for inside the GPU, but they are aiming to develop a quite aggressive capacity relatively soon. And obviously, NVIDIA and TSMC are developing silicon photonics. So they have this capability. They're investing probably billions of dollars into it. This is the first step on something that I think could be pretty exciting. So the other side of this is that we now have optical communication happening. Could we have optical computation taking place? And there's some good news among lots of bad news. And the good news is that inside most neural networks that you're interacting with on a daily basis, most of the computation, even today, is linear algebra. And there is a fundamental, from physics, advantage of using linear optical systems to perform linear algebra. And the way to think about it is that if I have a passive optical system like a lens, and I have n input modes that I prepare, so amplitudes of n laser beams, for example, and I measure n output modes, right, n photodetectors, the cost for sending light through the system scales linearly with the number of laser beams, right? It's linear in n, right? N laser beams. But the cost for light to propagate from this laser beam to that wall is completely free, even if all those modes have been coupled in general to fully connected matrix vector multiplication. In a digital system, actually this cost is n squared, because you have to do all of those operations, all n squared of them. And what this means is that as you increase the vector size, optics eventually could get to a point where it has an energy advantage over electronics, even though it is immature and there's overhead costs to get into the optical domain. But it's not clear whether or not this fundamental energy scaling advantage actually applies to realistic optical neural networks, including all the digital electronics and memory that is going to be around them. So with Maxwell Anderson, who's a PhD student at Cornell that I interacted with during my postdoc, we considered a realistic simulation model of an optoelectronic processor performing transformer neural networks. Now, this is a simulation, to be clear, so it's not as if this is a full-scale system. I'm certainly not guaranteeing its results to be true, but we did try as much as possible to consider all the fine print in realizing an optoelectronic computer in which the linear algebra is performed using optics. And the punchline of that work is shown here. This is the energy per inference as a function of the model size, the number of multiply and accumulate operations. And the main thing to take away from this is that for digital electronic processors, you see a different slope on this curve, a different slope on this plot versus the optics-based implementations. And what that shows, or at least implies in this case, for this specific architecture, for this specific context length, we see an advantage for optics. So it turns out this is somewhat sensitive to the details of the architecture, so it's again not a guarantee. And of course it will depend on what is actually realizable here. But it shows that there's a potential for this fundamental scaling advantage in simple linear algebra to translate to realistic, attractive, large-scale neural network inference. These are existing demonstrations. So these are calculated models that we have projected. right? No one has made the future for quadrillion parameter model yet, but that was projected along the trend of models that we saw down here. So the punchline here, the summary, is that optics provides a fundamental scaling advantage in performing linear algebra. And this appears to translate to realistic optoelectronic hardware and large-scale neural networks like large language models, and appears to is bolded there. And to overcome the overhead costs associated with reading from memory and converting from digital to analog and optoelectronics, going from electronics to optics, we're probably going to need to target very large vectors. And I think that number is probably larger than 1,000. So the second point I want to make is that if photonics is capable of doing computation, it would allow us to do a range of things that are not currently accessible with computers. And I'll give you one example of that. This is work that was led by Tianyu Wang, now at Boston University, and Mander Sahoni, who's a PhD student in Peter McMahon's group at Cornell. In a conventional machine vision system, you have a camera, a high-resolution camera, that captures an image of a scene, and then you post-process that high-resolution image using a neural network, for example, to extract a small amount of information from that. And the important thing is that for most tasks, the amount of information that you extract is a small fraction of the information that you need to collect in order to extract that. So what we did, which is a common theme in the literature now, is we put a neural network, in our case a nonlinear optical neural network, in front of a camera, and we used this optical neural network to extract the information of interest and to compress that information into a smaller dimensional latent space that allowed us to use a smaller sensor array and less digital post-processing. This allows you to go much faster. You can go faster by the ratio of the number of pixels, and it also opens the possibility of being sensitive to features of these photons that would not normally be available. For example, here you can only measure the amplitude and RGB color bands, but here we could be sensitive to all of the different frequency components, right? We could have much higher spectral resolution. We could also look at polarization or even quantum properties, as a recent paper from Mandar has explored. So if everything goes well, photonics could be integrated into this virtuous cycle, and of course we would see the elevation of this technology into sort of dreamlike territory. So this is what it could look like. Better photonic systems, better electronic systems, and better optoelectronic systems would then allow for more compute per dollar. And that would be good for existing computer companies because it would extend the existing virtuous cycle of it creating more value for existing customers and creating more customers. But also, and I think this is an underappreciated point, as you add physical substrates to the virtuous cycle, you are also expanding the space of applications that these computers can serve. And that image sensing is one example. Of course, you can really think broadly about what you can do with these systems now that they're embedded in the analog physical world. But the key is that at this point, better photonic electronic technologies lead directly to more resources and demand to make better photonics and electronic technologies. It's that feedback loop that needs to be established. So I've given you this rosy picture of dreams and promise, and I now want to dash those by telling you why this is probably not going to transpire. The first thing, and most importantly, is that digital electronics has a huge lead on photonics, and this is a moving target where there are lots of smart people in digital software and digital computer architecture that are advancing this every year. There are also many other up-and-coming technologies, including superconducting and analog electronics, which might be an easier pivot from existing digital electronic infrastructure that could also offer advantages. The wavelength of light is large, so it's actually quite difficult to imagine making complex photonic systems because of the fact that the wavelength is 100 times larger than electrons. As Dimitri pointed out in his talk, photonics does not have good solutions for nonlinearity in memory, so it's not going to provide universal computation anytime soon. Photonics is noisy and analog, and this is kind of a big problem when digital computing has been absolutely essential to get to the scale that we have in digital electronic systems today, right? We wouldn't have computers if we done them in an analog way. There's also a lot of talk in data center energy innovation. For example, putting data centers on the moon, or perhaps under the ocean, or building nuclear power plants near data centers. And you might laugh at some of these, but other people laugh at doing photonic computing. It's not clear which one is more laughable, and the one that is least laughable will ultimately be the winner. Now, I think the thing that is most concerning, and that is already happening, and I was really pleased to see Natalia's talk address this, is that actually algorithms are changing, right? As soon as we think that there's an algorithm that is favorable to our particular hardware platform, there are people who are developing algorithms for computers, for GPUs, for data centers that already exist, and they are not making those algorithms so that they are good for our hardware. They are making algorithms that are better for their hardware. And as a result, we're chasing this algorithm that is getting further and further away. Another important thing is that based on the size of companies that have attempted and so far failed to produce this or get close to it, I think that there will be a huge investment required, probably many billions of dollars. And this then enters into the world of politics and the economy, which is quite hard to predict. Any sort of short-term instability in the market or an AI bubble bursting would also penalize high-risk technologies like photonics. And then finally, didn't optical computing actually already fail twice? Not everyone in this room might be old enough to know this, but this isn't the first time we have tried this. But it is different this time in at least a few ways. And I think these are quite notable. It makes me optimistic that it might work this time. The biggest one by far is the fact that major companies like NVIDIA and TSMC are developing co-integrated silicon photonics first for interconnects. We also have significantly more capable integrated photonic systems. And electronics are closer to their fundamental limits, although this has been said for decades and it never seems to be an actual important feature. What is perhaps a more important feature is that AI calculations are much, much better suited to noisy analog hardware than just about any calculation that has been considered before, and they are now a driving force for the shape of computer architecture, right? You saw this Cerebus chip. I'm going to show you some examples later. This is doing these calculations is driving the design of computers. And normally in this talk, the second half would be about quantum photonic computing, which shares a lot of the same infrastructure and could be cooperating with classical analog computing in a way that could make these two get over threshold. But the important thing here is that it may not work, right? These are all reasons to be optimistic, but I don't know that we are going to actually get this to pull off. So in part two, I want to quickly talk about how I think we can make this happen. And so when you develop a new technology, there's a big step between that technology being successful in your laboratory and it actually having an impact in the real world. And there's a specific kind of person that is not in this room as far as I know, but they have everything to do with this. And they look like these two gentlemen here. They are business people. And when I talk to physicists, I notice most of them don't have any idea how these people work. So I have good news for you. I have a physical model. This is a toy model for how business people work. And it's based on one assumption. I call it the efficient allocation hypothesis, which is related, by the way, to something called the efficient market hypothesis, although it's a slightly generalized version. And that says that business people will tend to distribute their time, their energy, their attention, their money to areas of maximal perceived profit within some abstract space of technology business models. And you can kind of go crazy with this, and you can formalize it if you like. But the main thing is that this ensemble of business people is going to follow this perceived profitability landscape. And we, in academia, have the power to shape that landscape. So with this insight in hand, the question is, how do we go from here to here? Well, there's this activation energy to get over. But you can calculate the Kramer's escape rate from this paradigm to this paradigm. And the important thing is it depends exponentially on this thing that we can control. And we actually have two knobs. We can either reduce the transition cost, so we can make it more profitable to be in this no man's land here, or we can make the new niche more attractive. And I'll give you some examples of both. So optical interconnects are lowering this transition cost because they're helping to develop the technology that would allow us to do this. One thing that my group is pursuing, which is following on work that I started during my postdoc at Cornell, is to make optical processors using programmable multimode waveguides, which we've shown can scale to 1,000 dimensional matrix vector multiplies, and to manufacture them using a process that was developed for displays. And these are displays that were developed for AR and VR systems. So we're able to co-opt this process. We don't have working chips yet, but if it works, this is a scalable approach to realizing 1,000 dimensional or larger matrix vector multiplies using optics. We've also created nonlinear versions of this technology that allow us to program in a multimode waveguide or multimode wave propagation the Chi2 nonlinearity as a function of space. This is work in Peter's group, led by Ryotatsu Yanamoto. And this allows us to use this kind of infrastructure, not for computing, but for doing basically an FPGA for nonlinear optics. And you can think about this as allowing us to utilize this developing technology to do other things like generate different kinds of light sources. I'm not saying that this is going to be a huge market, but it doesn't directly compete with the GPU. So there are ways that we can push this down. Another thing my group has been working on is going beyond linear algebra. And recently we've been able to show that if you have a programmable nonlinear optical system operating on many different modes of light propagating through it, and you can program this in space, you can actually perform arbitrary higher order tensor contractions. So third and fourth order tensor contractions for Chi2 and Chi3 nonlinearity respectively. And the important thing here, all the details need to be determined, is that these allow you to perform computations that give you a larger scaling advantage relative to electronics. And rather than 1 over n, you get 1 over n squared or even 1 over n cubed. So this could potentially make this more attractive. So in the remaining time I have, which I know is not very much, I want to zoom out and talk about what this looks like for PNNs in physical computing more generally. So we're here, but for the whole space of physical computing, what does this techno-business space look like? Well, I think that the first local optima to aspire to are what I call single-purpose physical neural networks that I'll explain. And what's over here, I'm not sure. Maybe Sam's talk will talk about physical learning machines that could be a scalable way to large-scale analog systems. Or Dirk sort of gave this dream of automated inverse design of everything, which I'm quite sympathetic to. But I think that this is a more accessible near-term thing. And one reason for this is that we are now utilizing foundation models. And these are neural networks that are trained on a vast corpus of data and then used to do a wide variety of downstream tasks. All the neural networks that you interact with on a daily basis are based on foundation models. And these foundation models are next word predictions, next token predictors, which means that when they generate a whole bunch of text, they have to do inference every single word. Moreover, nowadays, we are not just utilizing this in a one-shot way. We are actually extending this inference using methods like chain of thought or generally reasoning methods that cause the model to do a whole bunch of these inferences, to sort of think out loud for a long period of time. And collectively, all these things mean that we're taking one model, we've trained this one special model, and we're going to do a ton of inference with it. And so this means that actually there's a path that it becomes more attractive to consider single-purpose physical neural networks. So there's development on new computer hardware, like the Cerebus chip or the Gronk chip, which are not physical analog computers at all, but they are specially designed to do AI inference. There's a recent demonstration by the company Thales, which encodes weights in read-only silicon memory. And this was considered to be kind of a flashy demonstration, in some ways superior to what is possible in GPUs. More recently, there's been a proposal of essentially completely hardwiring a digital electronic neural network, literally putting the weights within the 3D topology of the wires that access the memory. And what I've recently proposed with Tatsuhiro Nodera, Taeyanyu Wang, and Peter McMahon is the logical, or again, possibly illogical limit of this theme, where you implement the entire foundation model inference in one physical analog system that is not programmable, that has just fixed parameters. So the idea looks like this. Imagine once a year when there's a new version of Claude or Opus that you're excited about, that will get burned into some physical substrate, and that will go onto a chip surrounded by digital electronics that sort of stewards it through various applications. In the archive paper, we consider an example based on nonlinear optical wave propagation through an inverse designed structure that has a refractive index that can vary in 3 dimensions. And this is a nonlinear pulse propagation situation, so it actually is likely to be universal to do all the operations required, for example, in transformers. I was inspired by 3-dimensional data storage, right? This is work from Eric Mazur's group that goes back now 30 years. But I'm hoping maybe Alina's talk tomorrow will also offer some possible manufacturing strategies. But here the punchline is that with this fixed optical system, right, this non-programmable optical system, we can actually imagine doing, with back-of-the-envelope calculations, much better than the equivalent calculations would suggest for digital electronics, right? So these are not experiments. These are back-of-the-envelope calculations, right? This is a closed-packed cube of GPU chips, right? This is a volume that is limited by the size of parameters. So these are not demonstrations. They are a proof of concept. But it allows you to scale these systems up to longer and longer, larger and larger systems that could allow you to go to even larger neural networks. I spent a lot of time trying to figure out how you could do this with electronics. It's actually quite subtle to imagine getting a system that is sufficiently expressive. And what I concluded is that we would have to do something like this, have nonlinear electronic transport in which we engineer the resistivity as a function of 3D space, basically the analog of the 3D optical device. But this is an incredibly difficult inverse design problem, although it's one that I think is pretty exciting. So there's many problems with this approach. One is that even though you don't necessarily need large-scale inverse design, you still need a compilation procedure to take this model and put it into this fixed physical hardware. And that needs to be tolerant of manufacturing errors. And these errors that build up over the course of a nonlinear analog computation are, of course, a grand challenge that no one has so far devised a good solution to. Manufacturing of something like this is not trivial, especially in 3D. And something that I discovered in considering this, and that I think is a really interesting problem for all of us to think about, is that actually I'm not sure that this would be very safe. Each one of these models would be its own individual thing because it would have variations, and it will degrade over time or be sensitive to temperature, right? It will have its own moods, and it will have its own ages. So I'm not sure that these would actually be systems that I would, subscribe to using. And I'm not saying any of these things are easy. I'm just saying that it might be easier than also solving weight movement and training simultaneously. If PFMs were available, it would open up many different ways of scaling physical AI systems, right? You could imagine doing extreme test time scaling, asking it to think for an entire century, because you could do this very quickly. You could imagine having digitally managed sort of corporations of PFMs, where you have digital systems that orchestrate the behavior of many different fixed physical foundation models. And perhaps there are also ways to think about AI safety by noting the fact that this system is actually grounded in the physics of its evolution. So this is the talk in one slide. And the last thing I want to say is that although I've talked a lot about engineering and applications, I do want to echo something that I've heard in some of the conversations here, which is that although we have quite an opportunity in this field to have an impact on one of the most pressing economic problems and opportunities in the world, I still think that this field is actually mostly a scientific field. And I mentioned that at the beginning, and I hope we can get more into it in the panel discussion later. Thank you.
Questions? Yes.
Thanks for the talk. So I was wondering, when you showed the scaling of the electronics versus the optics, how did you incorporate precision into this? So this is like for the same precision?
Yeah, so it's for the same precision. It's for precision that was calibrated on an actual optical linear algebra processor based on a spatial light modulator. So this was, Maxwell went into the lab, he collected data doing samples, sections of this transformer neural network, and he looked at the precision that he could achieve, and he used that precision, which is about 6 to 8 bits, as the comparison. So these are apples to apples in terms of precision.
Thank you for the great talk. So regarding the last point about the physical foundation models,
Yeah.
It didn't quite come clear to me what's the nonlinearity involved.
So of course it would depend on the physical system. In the system that I considered, this is just fused silica glass with a Kerr nonlinearity. And the limiting constraint on the energy is actually the amount of pulse energy that you need to have a pulse that will get sufficient nonlinearity as it propagates through that glass. So this is a back of the envelope calculation, but it's really trying to avoid assuming anything exotic or unusual. So these are, I think, nanosecond duration pulses that need to have a high enough peak power that there's going to be a lot of nonlinear phase accumulation over this device.
See, it violates somehow one of the tenets of Demetri's talk.
I know.
There was a third question, I think.
Yeah, great talk. A lot of nice philosophy. But he touched it a little bit, but I think there's a difference in approaches that have discrete components, you know, or something like I assume like the last thing you talked about, it's continuous somehow, both in X and Y and Z and also in amplitude analog systems. I find it hard to calculation with discrete devices to make it look, because the wavelength is so huge. What do you think about that? You think there is continuous analog world to? I think that's the only way I can see optics having an advantage.
I agree. I think that for optics, because of the scale of the wavelength, you basically have to have a system that is completely composed of parameters. There's no other way to imagine this fitting together. And you see here, we already had to go to 3D. So I'm open to somebody coming up with a solution, but I don't think the discrete components thing is going to scale. It requires a chip that is too big. Electronics is a different story, of course, but in optics, I agree. I think it has to be this continuously programmable system.
Going to deep UV is also
Yeah, I agree.
It's far.
I have to admit, I wanted to ask the question 50% because of this throw and catch. Just the question, so for this big systems now, the 3D nonlinear one, I mean, what is your feeling for the training? I mean, do you think we will have a chance to do this in silico eventually, or is in situ the way to go?
So, I mean, I'm saying something that could be controversial, but I'm saying I don't think that physical learning makes sense for solving the problem of beating a GPU. I'm saying physical learning is not a good solution. I agree with Dimitri that fixed is better. These things would not be designed by in situ training. They would need to be designed by taking a pre-trained model, like the existing version of Opus 4.8, and compiling sections of that one by one into equivalent optical analog computation. right? So you wouldn't inverse design this whole thing. You would take sections of a pre-trained model, tiny sections, and then you would train those all together. You know, you have this conversion process, which could be based on inverse design, but wouldn't need to be. And then you'd compile them all together and then maybe do some fine-tuning.
Got it. Thank you very much.
Behind you.
One last question.
Great talk. I'm wondering about that. You had that scaling plot with had the like actual models on there and the energy costs, and they seem to be below the lines that were theoretical.
Yeah, that's right.
As in, they're using less than the kind of idealized GPUs.
So the GPU projections that we put on there were, you know, to not make this overly easy on ourselves. Yeah, we've assumed GPU projections that are better than any existing GPU here, right? There's no GPU that is here.
Right, but aren't you saying that existing models, or are those existing models if you ran them on your?
These are not attached to any. These are existing demonstrations.
Right.
Right, and then these dashed lines are theoretical projections. So there's not; those are two different.
Right.
Data
Maybe
points.
I'm being really silly, but aren't the demonstrated ones better than the theoretical predictions?
So this is a line of best fit.
But like GPT-2 base is using less energy than a theoretical, like ASIC FPGA, or is that an existing one?
So which line are you referring to? This line or this line?
So the ones above that are existing. It's the one below it. You're saying that's not.
So this line is not possible to achieve.
Okay.
Right?
Okay.
Right. This line is like attached to this thing, which is not currently available. Right. These are consuming less energy than these plots, than these lines here, but those lines are to show the slope.
Okay. Okay.
Right. So they're not like, we're not drawing them through here because it would be kind of messy to plot everything. It's already the most complicated plot I've ever seen in my life.
Thank you.
All right. Let's thank Logan again and all the speakers.